Well, let us consider now the problem of a pendulum with a moving support. Now, first, the solution of part A. We will consider first that the point, the mass point, moves along the support, move with displacement, 8 times omega t, sine 8 times sine omega t. The position vector of the mass m is given by this vector, the position in the x direction plus the position in the y direction, where theta is the angle between the vertical and the pendulum rod. The mass velocity is just the derivative of the position with respect to t, to time. This is the result. We will apply Lagrange mechanics, so we need to calculate the kinetic energy. The kinetic energy is 2 times m mass times velocity squared. This is the result. We take the square of the velocity. We do some calculation, algebraic calculation, and then we get this nice result for the kinetic energy. The potential energy is minus m times the gravity times the vector position. The gravity is along the vertical, and the position, this is a scalar product, so just the term in the vertical is with the result we get minus n times g, acceleration of gravity, times L cos theta, cosine theta. Therefore, the Lagrangian of the system, which is equal to kinetic energy minus potential energy, will be all these nice result, nice term. Now we will try to find the equation of motion for the mass of the pendulum mass, using the Lagrange equation with the notation dot theta equals derivative theta with respect to t. We need to calculate this partial derivative, the Lagrangian with respect to theta, the partial derivative of the Lagrangian with respect to dot theta, and then take the derivative with respect to time to the partial derivative of Lagrangian with respect to theta dot. We do all the calculation. Here are the calculation for the partial derivative of the first with respect to theta, the partial derivative of the Lagrangian with respect to dot theta, and finally the derivative of the Lagrangian with respect to the dot theta. Now we put together all these results into equation 8, and we get all these equations, long equation. But as we can see, this term cancels with this term, and after some little algebraic manipulation, we get this equation. This is the equation for the mass, for the pendulum, but with a support moving in the x direction with we can see that we can say that the moving is the support of the mass is moving along the x direction with harmonic oscillation. Simplifies. Now let us get on let's try to get the second part. And the second part, we need to linearize equation 10 in the limit of very small oscillation. Theta is very, very small, so Sine theta will become just theta, and cos theta will go to 1. So in this equation 10, cos theta is 1, and sine theta is equal theta. Then equation 10 becomes this linear second order ordinary differential equation. In order to solve this equation, we need the initial condition. Remember that the initial condition for the problem are the theta, the angle at t equals 0 is 0, and the velocity derivada de theta with respect to time is equal 0 also at t equals 0. The problems ask to solve this equation using Laplace transform. So we will apply Laplace transform to this equation. Remember, we will also using the dimensionalization in which L equal G equal A times omega squared. So this equation 11, becomes just simple this one. Second derivative of theta with respect to time squared plus theta equals sine of omega t. Now, we will apply the Laplace transform. We need to multiply all the equation, both sides, by exponential e to minus xt, integrate from 0 to infinite. If we do this, all this equation, the second term is the Laplace transform of theta. We call it theta x. And the first term, and on the left hand side, and the term on the right hand side can be integrated using integration by parts. The term of the left hand side becomes just s squared multiplied by the Laplace transform of theta x. And using integration by parts again, the term of the right hand side of equation 13 becomes equal to omega divided by omega squared plus x squared. Now, we will substitute in equation 13, the first term is equal to s squared Laplace transform of theta. The second term is Laplace transform of theta, and the term on the right hand side is this one, omega divided by omega squared plus x squared. If we do that, we get this. So the Laplace transform of theta, we call it theta x, is equal to omega divided by omega squared plus s squared times x squared plus 1. This is equation 14. We can write it this way. And we will use now convolution. Using convolution, this can be the equation 14 becomes this equation minus integral, remember convolution. I will try to show you later how to do this with, remember this is our ut and ut here, u tau here are ones. So the equation for theta t becomes the integral from minus infinity to infinity sine omega tau multiplied by times u tau times sine t minus tau multiply ut minus tau differential tau. This equation, remember, will transform to this one, to equation 18. But look carefully. Now, the limit of integration are 0 and t. And the integral, we need to integrate from, the integrand is sine omega tau times sine t minus tau differential tau. The inverse transform So the solution of our second order ordinary differential equation, linear differential equation, will be this one. This is the solution in the case of in which omega is equal 1. This is the solution if omega is equal minus 1, sorry. And this is a solution if minus omega is in the interval minus 1 to plus 1. This nice solution is obtained using MATLAB toolbox, symbolic toolbox. I will try to show you in another video later how to do this with MATLAB toolbox, symbolic toolbox. It's very easy and very it's worth to learn this application for MATLAB. So this is our solution for the nice problem of a pendulum with a moving support. Thank you.